Have you ever imagined what life was like on Earth millions of years ago? Do you know how different the planet, the oceans, and the creatures that lived there were from what we know today? To give you a glimpse of this distant period, today we're going to explore the Ordovician era. It's a fascinating and mysterious period in the planet's history, and one that has only recently begun to reveal some of its previously deeply buried secrets. Dear traveler, welcome. Today we're taking a trip back in time to find out how life developed and multiplied, despite obstacles that may seem insurmountable to ordinary mortals. Life, which exploded during the Cambrian period, the most recent period since the formation of the Earth, is about to undergo a new phase. Between ice ages and extraterrestrial phenomena, we're going to discover just how much our current existence might not have developed in its contemporary form, if at all. But before you set off on a new adventure that will take you, among other things, into the depths of the Paleolithic oceans, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! The Ordovician is the second period of the Paleozoic, the era that preceded that of the dinosaurs. It began 485 million years ago, just after the Cambrian-Ordovician extinction, which saw many living species abruptly disappear. Before 1879, the Ordovician was not yet recognized as a period in its own right. The Cambrian and Silurian periods followed one another. But a debate had been raging in the world scientific community for almost 40 years, as certain fossils found in the respective strata of these two periods had no proven link with them. It was Charles Lapworth, a 19th century British geologist, who finally settled the issue by interposing a new system between the other two, the Ordovician. The name of this period was borrowed from the Ordovices, a Celtic people from present-day Wales. Thanks to an in-depth study of sedimentary rock layers, he was able to demonstrate that they are far more complex than they appear. After extensive mapping work, he was able to confirm that these fossils, mainly composed of graptolites, belong to an intermediate period due to their location and arrangement in the sediments. The Ordovician period is divided into 3 eras with 7 distinct stages. From 485 to 471 million years ago, we find the Lower Ordovician, which includes the Tremodocian and Floan periods. This is followed by the Middle Ordovician, from 471 to 460 million years ago, with the Dapingian and Darawilian. The Upper Ordovician completes this period from 460 to 444 million years ago. The latter is made up of 3 stages: the Sandbian, the Cation, and finally, the Hernantian. But why, and above all, how can we divide this distant period into several parts? During the 41 million years that make up the Ordovician, certain species appeared at very specific times. It is their successive discoveries, and in particular their dating, that have made it possible to establish the chronology of these 7 stages. The oldest, the Tremodocian, is defined by the arrival of the conodont species Leptognathus fluctivagus, now extinct. This specimen is distinguished from contemporary conodonts by the lateral orientation of its main tooth-like projections. Traces of this fossil have been found mainly on the American continent, in Kazakhstan, and in China's Hebei province. The second stage, the Floen, marks the appearance of the graptolite Tetragraptus approximatus, an easily recognized H or X-shaped filter feeder. Traces of this specimen can be found almost everywhere in the world, with the exception of the UK, Africa, and Spitsbergen, an island north of Norway. The Dapingian stage, which heralds the beginning of the Middle Ordovician, corresponds to the first date of appearance of the conodont species Baltoniatus triangularis. The next stage, the Darawilian, is marked by the appearance of the graptolite Undulagraptus ostradentatus. The Huanghuachang section near the city of Yichang, China, is recognized as the world's reference stratotype point for these 2 stages. Finally, the Upper Ordovician saw the successive emergence of the graptolite species Nemagraptus gracilis, Diplocanthograptus caudatus, and Normalagraptus extraordinarius in the Sandbian, Cattian, and Hernantian stages. Their stratotypic reference points are in Sweden, Oklahoma, the USA, and China's Hubei province. The Ordovician has left its mark all over the globe. It allows us to establish how the continents were laid out at this time in the planet's history. Geologically speaking, the Earth changed little between the Cambrian and Ordovician periods. Land masses are still mainly located in the southern hemisphere. The northern hemisphere is still almost entirely covered by the waters of the Panthalassa Ocean. Only the continent Siberia and a small part of Laurentia have found their way into this hemisphere. The supercontinent Gondwana, partly covered by shallow seas, occupies almost the entire southern hemisphere. It includes South America, Africa, India, Australia, and Antarctica. In the intertropical zone, the 3 small continents that have recently formed, Laurentia, which corresponds to North America, Siberia, and Baltica, lie in the tropics. Numerous volcanic arcs are scattered around, mainly bordering the coasts of the Lapitous Ocean, and a newly formed ocean, the Reik Ocean. The opening of the latter further south between the Baltic and Gondwana initiated the closure of the Lapitous Ocean, but also the displacement of the supercontinent, which gradually moved away from the equatorial latitudes towards the South Pole. During this period, orogenic activity is very low. The mountain-building process was therefore limited to a few collisions between island arcs or ribbons of microcontinents against the south coast of the Laurentia continent. At most, a few small terrains or pieces of the Earth's crust, which detached from this megacontinent during the Lower Ordovician, will become attached to it during the Middle Ordovician. This geological phenomenon is known as the Taconian orogeny. It corresponds to a folding phase that lasted almost 10 million years before giving rise, after a long geological process, to the assembly line known today as the Appalachians. The separation of the continents reached its climax during the Middle Ordovician, the period of the Paleozoic era with the greatest number of continents. It was only much later, at the end of the Paleozoic, that they began to come together again. The Rheic Ocean Ridge showed strong activity at the beginning of the Ordovician. This led to the overflow of oceans into continental surfaces. It was during the Middle Ordovician that sea levels peaked, reaching, according to some estimates, 200 meters or 650 feet above today's values. While the tropical zone is the widest of known fossil times, by the end of this period, the supercontinent Gondwana had taken root at the South Pole, where it was gradually covered by an imposing ice cap. By studying the many fossils discovered in different parts of the globe, scientists are able to conclude that major climatic variations occurred during the Ordovician period. A considerable rise in sea level, as well as the proliferation of life in marine ecosystems over a given time, corresponding to the Middle Ordovician, demonstrate that drastic climate changes took place during this period. Similarly, the sharp decline or even extinction of many species suggests that some of these changes were probably rapid, leaving little or no opportunity for existing organisms to evolve serenely. During the Ordovician period, the climate was warm and tropical, especially during the lower Ordovician, when temperatures were at their highest. Some parts of the globe experienced record temperatures close to 60 degrees Celsius or 140 degrees Fahrenheit. However, towards the end of the period, around 445 million years ago, these temperatures began to fall, leading to a major ice age. The main continent, Gondwana, was gradually covered by a massive ice cap. This glaciation, which lasted approximately 1.5 million years, triggered the disappearance of a large number of animal species that were unable to adapt to the new environmental conditions. Thus, the Ordovician is a geological period characterized by the concomitance of a major ice age and one of the 5 greatest mass extinctions in the history of our planet. Indeed, despite tropical ocean temperatures that seem to exceed 30 degrees Celsius or 86 degrees Fahrenheit, the Ordovician left numerous indirect clues to the presence of ice on the continents during this same period. In an attempt to understand the mechanisms inherent in this climate change, scientists have turned to a computerized tool. They used numerical modeling that brought together several disciplines, namely meteorology, oceanography, and environmental physics. In this way, they succeeded in resolving the climatic paradox of this period. Comparison of the numerical simulations with a wealth of sedimentological, geochemical, and micropaleontological data suggests that the first stage in the growth of an ice cap occurred as early as the Middle Ordovician, more precisely during the Darwinian stage, as evidenced by the variations in sea level attested for the same period. These results indicate that the presence of a polar ice cap is not incompatible with high tropical ocean surface temperatures. gradual ice growth would then have allowed the ice cap to reach tropical latitudes, marking the onset of the Hernantian glacial maximum. In short, the Ordovician glaciation would have been a long-lasting one, of which the Hernantian, the last stage of the Ordovician, would in fact have been only the apogee. Thanks to a relatively warm climate, the Ordovician was a very prosperous period. Life already existing, but mainly located near the seabed, multiplied in an exceptional way. This period is defined as the event of the Great Ordovician biodiversification. During this relatively short period of only 25 million years, the oceans were truly filled with numerous families and genera of living organisms. There are many reasons for this unprecedented expansion of marine life. However, a key factor has been the increase in the surface area of continental shelves, particularly in the tropics, as well as high sea levels, all of which have encouraged the growth of phytoplankton, and consequently, of all aquatic organisms. These microorganisms have proliferated in the epicontinental seas, which are particularly extensive. Thanks to the abundance of phytoplankton, several groups of zooplankton made their appearance before expanding exponentially. These include Chitonozoans and graptolites. In addition, constant volcanic and tectonic activity during the Ordovician period most likely provided the nutrients required for the development of planktonic life in the oceans. As a result, the water column gradually filled with all kinds of living microorganisms, but not only. Indeed, the first fish made their appearance at this time, and cephalopods, the ancestors of octopus and cuttlefish, diversified like never before, to the point where, by the end of the Ordovician, ecosystems comparable to those of today already existed. This period marks the biodiversity plateau of the Paleozoic. Life became so abundant in the oceans that it eventually began to spread on land too. Fossils of spores, the microorganisms that form part of the life cycle of many bacteria, plants, algae, fungi, and even some protozoa, have been found in sediments attributed to the Upper Ordovician period. Similar to contemporary liverworts, these first land plants were most likely descended from green algae, already widespread during the Cambrian, the preceding period. Their proliferation was confined to shorelines and coastlines, where they formed a low-growing carpet. Among the fossils studied from the same period, others revealed the presence of the first terrestrial fungi. They certainly played a major role in the colonization of emergent soils by flora, making mineral nutrients available to plant cells through mycorrhizal symbiosis. Although these discrete plants are fairly primitive and basic, they mark a decisive turning point in the evolution of life on Earth. And while this stage is still in its infancy, it is no less important. It's the first time on the planet, after bacteria and other microorganisms, that a form of life is actually visible on unsubmerged soil. Thus, during the Ordovician period, the hues that brightened up the ocean floor began to timidly color dry land. Although this transitional period is decisive in our planet's geological history, it has long been overlooked. Indeed, until the early 2000s, only 2 major Lagerstätten, i.e. sedimentary deposits containing a wide variety of fossils, testifying to the Ordovician period, had been recorded. The first is located in New York State, USA. This is Beecher's trilobite bed, located in the Frankfurt Shale at Cleveland's Glen. It is associated with very particular environments, namely deep hydrothermal springs, in which low-diversity faunas dominated by a few arthropods thrived. Only 3 to 4 centimeters or 2 inches thick, this Lagerstätten revealed numerous trilobites in an exceptional state of preservation, particularly of their ventral anatomy and soft tissues, the latter preserved by pyrite replacement. This mineral, which is an iron sulfide, allows X-rays to be used to study the finest details of soft tissue anatomy. The fauna of this site is largely composed of the trilobite, Triarthris atoni. It alone accounts for 85% of the organisms studied. Other species include graptolites, colonial filter feeders, branched algae, brachiopods, and other enigmatic taxa. Among the many trilobite specimens of Cryptolithus, Bellulus, Cornoproteus beecheri, and Primaspis crocetus have also been inventoried. In terms of population, it belongs to the penultimate stage of the Upper Ordovician, the Cattian. The second proven Lagerstätten from the Ordovician to the 2000s was discovered in South Africa. This is the Soom Shale. It reflects the population of the Hernantian, the very last period of the Ordovician. Only the remains of pelagic organisms, i.e., those living in the water column, have been discovered here, thanks to their good state of preservation. These include arthropods, cephalopods, conodonts, and agnathan fish. However, these 2 conservation sites, like others, are far from providing as much information as those collected for the previous period, the Cambrian. All the more so as they provide new elements that only concern the end of the Ordovician. Nevertheless, as fossils are discovered, they continue to advance our understanding of this period. At the very beginning of the 21st century, in a valley in southern Morocco, north of Zagora, a major paleontological discovery revolutionized scientists' understanding of the earliest animal diversifications of the early Phanerozoic. This is the Lagerstätten Les Fezouata. The importance of the treasures delivered in this area even gives it the honor of being named by some the Ordovician Burgess Shale of Morocco. This storage site is an exceptionally well-preserved Ordovician deposit, but more importantly, it has yielded abundant and, last but not least, highly diversified marine faunas, some of which are attributed to the lower Ordovician. It has been selected as one of the 100 most important geological sites in the world because of its role in understanding Ordovician evolution. What makes the Fezouata site so remarkable is its predominantly clay formation, dating from the Tremodocian, the very first stage of the Ordovician. This clay deposit, estimated to have lasted almost 2 million years, contains a wide variety of fossils, making it possible to study the paleofauna. Fossils of carapace animals, similar to those found in the Burgess Shale dating from the Cambrian, have been discovered in the Fezouata clays. These have come as a surprise to paleontologists, who previously believed that this fauna had disappeared during the Middle Cambrian, some 40 million years before the Fezouata clays were deposited. This paleofauna also reveals crown group taxa, whose presence was unknown in the lower Ordovician. While the Fezouata fauna is dominated by trilobites, it also contains a high abundance of xiphosaurid arthropods, paleoscolicid worms, annelids, mollusks, brachiopods, and connular worms. Graptolites are also abundant. More recently, excavations at Taichoute, some 80 kilometers or 50 miles from the Fezouata site, have uncovered a new fossiliferous site. It differs from the Fezouata site in several respects. Firstly, it is a few million years younger. But above all, this site, which was once underwater, has preserved traces of large arthropods, described as giants. These, which may be related to modern creatures such as shrimps, insects, or spiders, must have been able to swim freely and move in currents. These organisms are in the minority in the Fezouata area. Given their colossal size, we imagine that they almost certainly dominated the seas 470 million years ago. Some specimens could measure up to 2 meters in length. They are therefore much larger than any specimens discovered to date. These giant arthropods, although not yet fully identified, may belong to species already discovered on the Fezouata coast. Their large size and free-swimming lifestyle suggest that they must have played a unique role in Ordovician ecosystems. If paleontologists can study mineral elements, they can also observe with precision the soft parts, which are in an exceptional state of preservation. At last, scientists are able to study the anatomy of the first animals the Earth ever sheltered. The carcasses discovered are thought to have come from a relatively deep marine environment, which is completely different from previous discoveries, where carcasses were preserved in shallow places. In addition, animals such as brachiopods were found attached to some fragments of these giant arthropods. This suggests that these large animals, once dead, served as nutrient reserves for seabed communities. The remains of Taichoute's fossilized organs enable scientists to map the marine environment of the early Ordovician period with some precision. The Ordovician remains a largely unknown period, yet it was a pivotal moment for the evolution and diversification of organisms that appeared earlier in the Cambrian period. While data concerning this period was relatively scarce, the discovery in 2020 of a new site, extremely rich in fossils, whose quality of preservation rivals the most renowned Cambrian sites, may partially fill the remaining gaps. This is the Castle Bank site, located in England in central Wales. Its sedimentary deposits and fossils date back to the Middle Ordovician, around 462 million years ago. More than 170 different species have been recorded, the vast majority of which are completely new to paleontologists. Unlike the Fezouata site in Morocco, the Castle Bank site contains a veritable miniaturized ecosystem. Indeed, most of the fossils are very small, measuring no more than 1 to 3 millimeters in length. they attest to a significant reduction in size compared with the previous period. However, their state of preservation is so exceptional that they provide researchers with a wealth of new information. Among the species studied, crustaceans, crabs, worms, sponges, and many others have left fossilized traces of their internal organs, such as their digestive tract, and even their nervous system. Soft tissues such as eyes, optic nerves, and even brains can be exploited. Likewise, the tiny, fragile limbs of arthropods are preserved, as are their sophisticated fine tentacles for filtering seawater. Among the specimens uncovered, some unusual groups of animals are brought to light. Opabenids, arthropods with a vacuum cleaner like proboscis, are described, as are wiwaxids, oval-shaped mollusks with soft bellies and backs covered with rows of scales. Other insect-like creatures probably distantly related to this category have also been described. Now let's delve into the depths of this period to take a closer look at these strange creatures. While the planet enjoyed a warm, humid climate, if the land was still bare and virtually barren of life except on a few shores, the shallow seas were teeming with life. Brachiopods were extremely abundant during this phase of evolution, still largely dominated by invertebrates. Brachiopods are animals with shells whose soft parts are contained between two valves. Although they resemble bivalves like clams, the body parts inside the shell are very different. What's more, their valves are symmetrically different from those of clams. A pedicle emerges from the larger of the two valves, enabling this brachiopod to attach itself to the seabed. Brachiopods are protostomans, one of two existing groups of bilaterians, along with Bryozoans. Bryozoans are mossy animals that live in colonies. They take a variety of forms, including arborescence or lace fan. Although they strangely resemble corals, they are not corals. Each individual secretes an arborescent calcium carbonate skeleton attached to a hard surface. Each specimen, called a zooid, usually measures less than 1 millimeter in length and lives in its own little lodge. All interconnected, they form colonies containing millions of zooids, which can grow to several meters in size. Within the same colony, each individual plays a distinct role. Some gather food, others help to strengthen the group. Finally, some of these individuals contribute to cleaning. To feed, Bryozoans create a water current that brings tiny creatures to their mouths. Most of the time, these are plant-like organisms such as phytoplankton. Bryozoans gradually colonize certain areas of the seabed, eventually building up into extensive reefs. Trilobites make up a large part of the Ordovician fauna. These crustaceans, which secreted an easily identifiable segmented exoskeleton, reached their peak during the Ordovician. In fact, they are the most famous prehistoric animals after the dinosaurs. Over 18,000 species have been recorded. They ranged in size from 1 to 70 centimeters or 0.3 to 30 inches in length. And their way of life covered the whole range of thalassic environments. Some were detritus feeders, grazers, or even predators. While a few species mastered swimming, the majority of trilobites moved along the seabed, burrowing into the sediment to escape predators. trilobites also developed the first advanced visual system. All trilobites had a head, called the cephalon, a thorax and a tail, as well as pairs of biramid legs on the ventral side. As with crustaceans, these legs had two branches, one serving as a gill for respiration, the other for locomotion and feeding. Among the most common trilobites, Cryptolithus measured around 1.5 centimeters or 0.6 inches in length, and Acidaspis nearly 2 centimeters or 0.8 inches. But there were also specimens of far more spectacular dimensions. These included the calamine, between 2 and 5 centimeters or up to 2 inches, and above all, the Isoletus, which could commonly reach 38 centimeters or 15 inches in length. However, the world's largest trilobite species ever discovered is Isoletus rex. Its complete fossil measures no less than 72 centimeters or 28 inches long, and 40 centimeters or 16 inches wide. The seabed was also covered by a large population of arthropods. Eurypterids, or gigantostracans, are one of the many species. They are also known as sea scorpions, for their shape is similar to that of modern-day scorpions. Eurypterids have elongated bodies extended by a long articulated tail. Its thorax is equipped with fearsome pincers, and its head features several pairs of eyes. A pair of legs that were intended to act as fins is terminated by large swimming paddles. Finally, most species are equipped with a tapering string at the end of the tail, which may well have served, if not to inject venom into some prey, to lacerate it. The size of Eurypterids was highly variable and probably depended on environmental factors, lifestyle, and taxonomic affinities. While the majority of arthropods were small-bodied and probably scavengers, the Eurypterid was undoubtedly one of the most feared predators of the Paleolithic oceans, commonly measuring a meter in length. Some of these specimens grew to over 2 meters or 7 feet in length. Megalograptus is another arthropod species. It is the oldest known Eurypterid. Of good size, the largest of the specimens discovered measures 78 centimeters or 31 inches in length. Like its congeners, it has spikes on its third pair of legs. Large spines on its various appendages helped it to locate prey, hidden in soft sediments and out of sight. Its telson, the last segment of its tail, if not venomous, probably helped it to tear its victims apart when feeding. During the Ordovician period, many new forms of echinoderms appeared, including sea stars, sea urchins, and crinoids. At that time, there were some 20 classes. While all present-day echinoderms have a pentarad configuration, i.e. 5 rays, this wasn't always the case for primitive forms, such as the carpoid, a strange specimen that still holds many secrets. Its truncated tail turns out to be a single arm at one end of its body. The animal's mouth is concealed on its underside. This single arm was probably as much for moving around on the seabed as for feeding. Given its morphology, it was probably a detritivore. The Ordovician period is also marked by the presence of large numbers of graptolites. These animals, living in colonies of 3 to several thousand individuals, belong to the Hemichordae phylum. They resemble coral polyps made up of coiled toothed tubes and are gathered around a main stem on which small cells shelter each individual specimen. These colonies of animals, floating or attached as the case may be, measure from 10 millimeters to almost a meter in length. The names of the different graptolite genera refer to the appearance of their branches and their number. Monograptus, for example, has a single linear branch, while Didymograptus and Tetragrammatus have 2 and 4 respectively. Spirograptus has a single spiral branch. Cephalopods are the dominant predators. Cephalopods lived in front of a long shell, called a chambered shell, because it was made up of several partition cavities. While some, like ammonites, had spiral shells, others were classified as orthoconic cephalopods. As their name suggests, they had a straight shell. This could be extremely large, reaching up to 6 meters or 20 feet in length, in the case of Camaraceras. Another species, Treptoceras, was usually around a meter long. Cephalopods were formidable predators, moving at will through the water column. It controlled its buoyancy by varying the amount of air in the various chambers of its shell. It was able to move by reaction, forcefully expelling the air contained in its body. Like a squid with a protective shell, this predator was at the top of the food chain. Thanks to its strong tentacles, it could dexterously capture any coveted prey, especially the trilobites that lived in great numbers on the sediments. All he had to do was carry his trophies to his mouth. This beak-shaped mouth was located in the center of the tentacles. In modern cephalopod groups, this shell has since shrunk considerably, or even disappeared altogether. Today, for those specimens that still have it, it is no more than a relatively small internal structure. Modern cephalopods include squid, octopus, nautilus, and cuttlefish. To feed all these little creatures, numerous mollusks line the seabed. Among them is the group of pelecypods, or bivalves. This group includes clams, scallops, oysters, and mussels. These filter feeders, which form shellfish beds, have 2 identically shaped valves on each of their body, and a laterally compressed burrowing foot. The upper edge of each shell usually has several teeth and sockets that fit into those of the opposite shell to form a hinge. Other mollusks also lived in large numbers on the seabed, gastropods. Snails and slugs also played an important role in this biodiversity. Unlike snails, slugs do not secrete shells, but they do have the same internal organs: a heart, a digestive system, gills, and a nervous system. Snails can be recognized by their unique coiled or spiral outer shell. The shell offered refuge from threats, which must have been incessant. The Ordovician seabed was also littered with corals, each more colorful than the last. Some were horn-shaped and secreted an exoskeleton that could grow up to a meter or 3 feet long, such as the Rugosa coral. Although this coral could be solitary, it could also form large colonies by grouping together with many of its companions. Like all corals, these are much more than just a stony skeleton. Inside, animals in the form of seeded polyps are evolving, as is their framework, which adapts to their growth. Equipped with tentacles containing stinging cells, they were able to capture their prey in suspension. While most corals captured and devoured their prey, they drew most of their energy from algae. Numerous varieties of round tabulate corals also carpeted the ocean floor, covered by warm, shallow waters. But the most extraordinary species is undoubtedly the crinoids. These marine animals gave their environment the appearance of a spring meadow. Indeed, they are commonly referred to as sea lilies. Belonging to the phylum Echinodermata, which also includes sea stars, sea cucumbers, and sea urchins, they display the pentarad symmetry, typical of echinoderms. Attached to the seabed by a long pedicle that can reach up to several dozen meters, they look more like flowers. Yet they were actually animals that fed with the help of podia, hollow cylindrical organs on their delicate arms that resembled the lightness of feathers. Food particles suspended in the ocean currents were captured by these arms before being placed in a furrow running through them. Then, like pistols, tiny cilia carried the trapped particles to the mouth at the center of the head. Among the invertebrates inhabiting the Paleolithic seabed, there are also those belonging to the sponge group. They played an extremely important role during the Ordovician period as reef-building organisms. Stromatoporoids are sponges calcified in layers called lamellae. Between each of these plates are vertical structures called pillars, as well as small distinct chambers called galleries. These galleries are lined with choanocytes, which serve to capture food and breathe while water circulates between the layers. Bumps are visible on the surface. These are nipples that probably contributed to the absorption and flow of water through this architecture. As fossils testify, stromatoporoids coexisted during the Ordovician period with many other species such as mollusks and brachiopods. Some shell organisms may even have been completely enveloped by a growing stromatoporoid, with some reaching 30 centimeters or 12 inches in diameter. However, these two species cohabited in harmony, with water flowing from one end of the stromatoporoid's porous structure to the other. Another sponge, with a very distinctive shape, also dominates the seabed. This is Brachiospongia digitata, a glass sponge. This siliceous sponge has a skeleton made up of a network of opaline siliceous spicules. Its cup-shaped structure features a series of 6 to 12 curved finger-like extensions. Finally, there is the Aulacera plumeri. This elongated organism resembles a trunk. Some of its specimens have probably reached 5 meters in height. We can imagine these animals living in colonies, giving the seabed the appearance of a more or less dense winter forest, through which prey and predators had to thread their way or even chase each other. Finally, the first vertebrates visible during the Ordovician period were agnathans. These fish are still the first vertebrates to appear on the planet. They are organisms that lack jaws and mandibles. Their mouths were slit-shaped, round as in the modern lamprey and hagfish, the only survivors from this period. Most agnathans had a cartilage skeleton and at least 7 gill pouches. These fish lacked paired fins and a stomach, but had a pineal eye, which was particularly sensitive to light. Agnathans could measure up to 30 centimeters in length. The plant world also underwent a number of diversifications during the Ordovician period. Encrusting, calcareous algae, green algae, and brown algae multiplied and diversified, to the detriment of cyanobacteria. Although cyanobacteria played an essential building role in reefs, they were gradually supplanted by corals and bryozoans. From the Middle Ordovician onwards, more precisely, during the Darwinian period that stretches from 467 to 458 million years ago, the fauna underwent great diversification. While no new phyla appeared, the number of families quadrupled, and the number of genera tripled. Pelagic animals were far more abundant than in the previous period, giving the seas the appearance they would retain throughout the Paleozoic. This vast diversification is probably explained by the drop in ocean temperatures, which were quite high at the beginning of the Ordovician, exceeding 45 degrees Celsius at the time. Indeed, temperatures gradually decreased until the Darwinian, when seas were comparable to today's equatorial seas, with waters around 30 degrees Celsius. Conditions for the development of life had then become particularly favorable, hence this great diversification. In addition, oceanic waters were enriched in mineral salts by the intense activity of ridges and by continental erosion, accentuated by the growth of terrestrial plants, especially as a large part of the continents was covered by shallow waters. These conditions favored the development of phytoplankton and algae attached to the ocean floor. As a result, food chains were literally boosted, encouraging the diversification of filter feeders, grazers, and primary consumers of all kinds, and then, de facto, that of predators. By the end of the Ordovician period, a quarter of all marine animal families and half of all marine animal genera had disappeared. This was the first great extinction of life, better known as the Ordovician crisis. But what could have happened on the planet to bring it to this point? According to scientists, the disappearance of more than 70% of all species is due to an immense episode of glaciation that the Earth underwent. According to some researchers, this biological crisis can be broken down into two extinction phases, spanning some 1 million years. A climatic cooling, triggered by continental drift, would have led to a drop in ocean temperature. Then, induced glaciation would have led to the formation of an ice cap, extending as far south as the high latitudes. Cold, oxygen-rich water would then have spread to areas previously poor in oxygen, causing the disappearance of organisms adapted to anoxic conditions. As ice expansion led to lower sea levels, oceans would have lost large quantities of water. As a result, organisms living in shallow waters would have suffered greatly. Then, at the end of this period of glaciation, rising sea levels would have triggered an expansion of the waters, this time warm and poorly oxygenated, leading to further extinctions. Another hypothesis challenges this explanation and suggests that this first of 5 Phanerozoic mass extinctions could be attributed to volcanic eruptions. Volcanoes are known to emit mercury. However, mercury enrichment of sediments has already been observed in other, more recent biological crises on the planet. A team of researchers therefore analyzed sediments, located in China's Hubei province, where the Wanggejiawan cut, a Hernanchian stratotype, is found. During the Ordovician, this region belonged to the Yangtze block, then covered by the sea. Black clays rich in graptolite fossils were deposited in an anoxic environment. Then, as the sea level dropped and the water cooled, clayey limestone covered these clays. The latter contains fossils of the Hernanchia fauna, characteristic of this ice age. The subsequent clays represent the post-glacial rise in sea level. However, it turns out that mercury enrichment was measured just before the clay limestone was deposited and persisted throughout the glaciation. A second enrichment occurred immediately before the arrival of the post-glacial clays. Similar observations were made in Nevada, when this territory belonged to an isolated continent, the Laurentia continent. Scientists have deduced that these mercury emissions correspond to peaks in volcanic activity. These two peaks of activity coincide with the two extinction phases of the Ordovician period. Researchers therefore hypothesize that eruptions attributed to supervolcanoes would have released gigantic quantities of carbon dioxide and methane, leading inexorably to a drop in Earth temperatures and the development of polar ice caps. For other paleontologists, the ice age that the Earth experienced around 460 million years ago could have been caused by a much more extraordinary phenomenon, one that is extraterrestrial in nature. In other words, winter came from the cosmos. A first hypothesis mentions a violent collision between two asteroids. The collision would have occurred in the asteroid belt between Mars and Jupiter, and its unprecedented violence would have shattered the larger of the two objects, which were over 150 kilometers or 93 miles wide, into billions of pieces. According to this hypothesis, the numerous fragments, some no larger than dust, others several tens of kilometers or miles in size, then began to orbit the Sun. The trajectory of the smaller debris changed and it gradually moved closer to our star, and consequently to Earth. 10,000 years after this extraordinary collision, the dust began to penetrate the Earth's atmosphere and scatter all around our planet. The result was a shower of fine particles that lasted for almost 2 million years. But after these tiny pieces of debris, larger and larger rocks, similarly deviated from their orbits, impacted the Earth. By analyzing numerous asteroid fragments in Ordovician rocks, scientists were able to date this event back 466 million years. In fact, the quantity of extraterrestrial dust is 1,000 to 10,000 times greater than in the sediment layers below this period. If debris from outer space regularly falls to Earth, the colossal quantities that reached it at that time cannot have been without consequence, and with good reason. Through this curtain of dust, the sun's rays had difficulty reaching the planet. Temperatures dropped considerably. Snow appeared at the South Pole and fell without interruption. As it accumulates, it gradually turns to ice. The South Pole is gradually covered by an ice cap, trapping a significant quantity of our planet's water. As a result, ocean levels dropped and winter set in on the planet. This winter will continue for millions of years. However, not all scientists agree with this theory, for while it is undeniable that an ice cap did indeed form at the South Pole between 467 and 458 million years ago, or even earlier, temperatures had already begun to fall by the beginning of the Ordovician period. What's more, for many experts, a veil of dust from outer space could not have influenced climate over such a long period. Other mechanisms probably contributed to this drop in temperature. What if the continental waltz had something to do with it? During the Ordovician period, 3 small continents drifted away from the megacontinent Gondwana. While the latter remained at the height of the South Pole, the smaller continents moved closer to the equator. Laurentia, Siberia, and Baltica therefore enjoy a tropical climate. The sun's scorching rays alternate with unparalleled precipitation. The carbon dioxide in the atmosphere is then precipitated by rainwater onto the continents or directly into the oceans. Under the effect of this heat and abundant rainfall, rocks are dissolved. They are then eroded by the ions released by this dissolution. Some of these ions contain carbon, which is also carried by runoff into the oceans, where marine organisms use it to build their shells and skeletons. Carbon dioxide is inevitably reduced in the atmosphere, so it no longer fulfills its greenhouse function. As terrestrial temperatures depend directly on the amount of carbon dioxide in the atmosphere, if the latter falls, so do temperatures. So, for some scientists, the cooling of the planet during the Ordovician period is explained by plate tectonics. Finally, another theory, albeit controversial, could explain this mass extinction. This is linked to the supernova explosion of a dying star, several thousand light-years from Earth. This explosion, which seems to have taken place over 440 million years ago, in the farthest reaches of our galaxy, generated powerful radiation energy, releasing an extraordinary quantity of gamma rays. After a long journey at the speed of light, these unfortunately hit the blue planet after piercing the atmosphere with unprecedented power. The impact was so violent that it annihilated the air molecules and swept away the atmosphere surrounding our planet. One of the first consequences was a chemical change in the atmosphere. Nitrogen and oxygen molecules were transformed into nitrogen dioxide. This brownish, particularly noxious gas eventually surrounded the planet. The planet was then no longer able to receive sunlight, causing temperatures to plummet. But let's put this into context and look at the various phases of this extinction, which have been extensively documented in a 2010 TV documentary. Before this supernova, life teems in the oceans. The sun was shining brightly under a radiant sky, and species were multiplying on a massive scale in tropical seas. For the first time on the planet, which is warm and humid, life seems to be gaining ground. Some species are even beginning to venture out of the water, particularly in the shallow, epicontinental seas. It's true that on the surface, paradoxically, life is hardly possible, and our world looks more like a wasteland, like Venus, for example. Oxygen levels are so low that no modern animal could breathe properly. Imagine the silence that must have reigned on the planet at that time. Absolute silence. But this Olympian calm is about to be disturbed by the supernova explosion of a dying star 6,000 light-years from Earth. Powerful radiation bursts from its poles. It's a gamma-ray explosion, the most violent phenomenon in the cosmos. In just 10 seconds, this supernova produces more energy than 1,000 suns put together. These gamma rays then travel through space at the speed of light. Despite its remoteness, planet Earth will unfortunately not be spared. But luckily, the cataclysm occurred far enough away that it didn't blow away our atmosphere and send it into the cosmos. Gamma rays are therefore able to penetrate the upper layer of the atmosphere. Like the northern lights, they produce a spectacle of rare beauty, but their impact will be decisive and above all destructive. Within seconds of the supernova, these lethal rays annihilate air molecules and blow away the atmosphere. A star of strange behavior stands not far from our sun, visible even in broad daylight. These are the remnants of the supernova, which will remain visible for a few more months before disappearing completely. At first glance, this distant cataclysm seems to have had little impact on life on Earth, and yet, in the hours that followed, extinction did indeed begin, but at a microscopic level. During their passage, the gamma rays destroyed 30% of the ozone layer, allowing the sun's ultraviolet rays to reach the planet. The light is so bright that it appears 50 times more intense than in the middle of the Sahara Desert. If terrestrial creatures had existed at this time, they would literally have been consumed in a very short time. The consequences of this biological disaster will begin to show in the water. Plankton, invisible to the naked eye, are the first to suffer. The sun's rays, which have become too powerful, burn off the vast majority of these microorganisms. Plankton is the basis of the food chain. Imagine the panic of plankton eaters as they watch their food run out under the devastating sun. Trilobites, whose larvae's main incubation site is the water's surface, see their reproduction diminish and even come to a halt. Nothing can survive the intensity of the sun's rays. Many corals and other animals quickly perish. A veritable domino effect leads to the collapse of the entire food chain. Tropical zones are the first to be affected by this particularly harmful ultraviolet radiation, and coral reefs are gradually dying out. Soon this phenomenon spread to the four corners of the globe, with corals succumbing to starvation. More and more animal species run out of food, and the reefs die out week after week. In the months that follow, the weakest animals are the first to disappear. For some, driven by their survival instinct, eating habits change. Predators accustomed to choosing their food must now make do with what they are lucky enough to find. Some even start eating corpses, something they would never have done before. Some species will eventually leave the dying reefs in search of food. This is particularly true of the giant orthoceras, the squid's ancestors, who have preferred to venture into brackish waters to devour new prey, the eurypterids. Famine rages. It affected all species, causing more and more extinctions. Biodiversity underwent an unprecedented crisis. If all the creatures in existence at the time had disappeared, what would have become of our planet? Would life have evolved in a completely different way? More on this later. In the months that followed, the scattered molecules of the atmosphere swirled around the Earth's sphere. As the atoms line up, they form nitrogen dioxide, a brownish, noxious gas. The bright sunlight is gradually masked by this thick layer of putrid air. After suffering the sun's wrath, the planet now receives only 50% of the sun's rays. Inevitably, the temperature drops to -12 degrees Celsius or 10 degrees Fahrenheit. Species that have survived famine until now are now faced with temperatures that are far too low. Nautiloids in particular are seeing their eggs laid a few months earlier fail to develop properly. The cold has slowed embryonic growth, encouraging the appearance of bacteria. The rare specimens that survive this compromised incubation enter a world of chaos. During their short life, they have only one objective: to find food. But these mollusks have a distinct advantage over many other species. Their bodies are totally protected by a shell that has enabled them to live in deep waters, sheltering from the devastating effects of climatic cooling. What's more, they have a varied diet. They are sometimes even labeled as opportunists, and have never hesitated to be scavengers. Animals that were able to move around, therefore, tried to reach milder areas. Unfortunately, during the Ordovician period, the majority of animals were sedentary, and the seabed was largely occupied by corals, brachiopods, sponges, and many other non-mobile species. Another problem associated with the lack of food is shell formation. The shells of most reef dwellers are made of calcium carbonate. Calcium carbonate is extremely difficult to secrete in cold water, which has inevitably led to the disappearance of many species. The planet's cooling has also resulted in a harsh and, above all, unpredictable climate. Before the supernova, the weather was always very stable. But for the first time in millions of years, major temperature shifts are triggering strong ocean currents. These generated violent climatic disturbances. The planet, hitherto relatively peaceful, is confronted with a Category 5 hurricane that sweeps across its surface on a permanent basis. Many animals, too weak to resist, end up smashed against the rocks. Those still able to fight try to find refuge in the depths, away from the surface waters, which are far too turbulent for them. But not everyone can escape the pressure of deep water. This is also the case for orthoceras, which, despite their titanic size, cannot find shelter there. Their disproportionately long shells are not designed to withstand such pressure. As a result, even the largest predator known to Ordovician times found itself in an awkward position. Nautiloids, on the other hand, thanks to their more robust shells, were able to find refuge in deeper, less turbulent waters during these storms. For dozens, even hundreds of years, these species suffered heavy losses. Corpses by the thousands washed ashore. More than 500 years after this event, from outer space, almost a third of the fauna became extinct, and the remaining creatures had little chance of surviving in these conditions. Life on Earth, in whatever form, was threatened with complete extinction. However, a certain number of individuals would survive and make it through the following thousands of years. Nearly 150,000 years later, life on Earth was virtually reduced to nothing. The species that survive this biological catastrophe are constantly starving. Orthoceras, once lords of the seas, are now weakened scavengers in a world that no longer resembles what it once was, especially as a new ice age begins. The planet is getting colder and colder, and snow is piling up at the South Pole, until over the centuries it has become so dense as to form immense glaciers, several kilometers or miles thick. These run along the length of the Gondwanaland continent, spreading further and further north. These glaciers trap a huge quantity of water, so much so that sea levels drop considerably, losing up to 60 meters or 200 feet. As a result, the shoals dry up completely, squeezing the life out of the few remaining communities. This drying up proves even more fatal than the gamma ray explosion itself. Some animals showed great resilience during this new ice age, in particular the Astrapus, the ancestor of all vertebrates. The first known vertebrate fish, this jawless agnathan, was able to follow the retreating ocean. Measuring around 10 centimeters or 4 inches in length, and equipped with large external bony plates serving as a shield, it withstood cold water better than any other aquatic creature. What's more, since its diet was not exclusive, it fed on whatever it could find. Carnivores, on the other hand, which fed strictly on a specific prey, found it much more difficult to feed, and many of these species became extinct. What's more, Astrapus didn't just adapt to its environment. In fact, a new variety of fish soon appeared. These now have bones and muscles that give rise to the first gills, making it easier to sort and absorb food. In this totally transformed world, Astrapus was not the only fish to follow the movement of the oceans. The Eurypterid, commonly known as the sea scorpion, also changed its territory, fleeing from the surface. It has even taken the place of the Orthoceras in the food chain, its main rival, which did not survive these extreme conditions. Since Astrapus was half its size, its need for food was much lower, a much more favorable factor for its survival. During this ice age, the planet took on a completely different aspect. Falling sea levels reveal new landscapes. The reefs created by sponges, corals, and arthropods were reduced to skeletons and partly emerged. The rare species that survived these reefs did not survive the cooling, especially as glaciers gradually invaded the subtropics. Gigantic icebergs drift through these former tropical regions, crushing everything in their path, including coral, thousands of years old. Year after year, sea levels continue to fall. Life is hanging on by a thread, but those still alive are struggling to keep up with the oceans, while aquatic habitats are becoming ever smaller. Unfortunately, the cascading consequences of the supernova are not yet over. Soon, the survivors will have to face a new climatic event, as more than 500,000 years after the start of this crisis, the planet is showing signs of warming. Glaciers are beginning to melt. Species that managed to adapt to this ice age will once again have to acclimatize to these new temperatures to stay alive. Some species stand out by adopting unprecedented behaviors. The Eurypterid is the best example. This sea scorpion, now the world's largest predator, began carrying the carcasses of its prey towards the shore. It even ventured onto land, as evidenced by the development of lungs found on certain specimens. Astrapus's cousins, the Acanthodians, have also developed jaws. They are no longer content to eat algae. These scavengers can now cut flesh and feed more easily. In this way, they moved up the food chain. In the course of this long adaptation, the roles were reversed. Predators became prey and vice versa. But no matter, life, fragile as it may seem, has endured. More than 3 million years after this extinction, it's time to take stock. And it's a heavy one. Over 70% of species have become extinct. According to scientists, nearly 1 million species existed before this mass extinction. This means that around 700,000 of them died out in this relatively short period on a global scale. All living organisms were impacted, bottom dwellers and pelagics alike. Yet its impact on the history of the living world was not so catastrophic, insofar as this biological crisis did not result in the total disappearance of any major animal group. Life proved to be extraordinarily resilient, beyond all expectations. At the end of this period, the Earth will gradually return to a tropical climate, giving the various animal and plant species a little respite. But will this respite be long enough to allow new biodiversification? I think you already know the answer.